Hello and welcome to TidyX episode 182. TidyX is a screencast where we go through and explain how our code works. My name's Ellis Hughes.
My name's Patrick Ward. Thanks for joining us for 182 episodes of TidyX. As always, be sure to like and subscribe. Drop questions down below on that YouTube channel. Might be able to get your question on the air, like the question for today. And as always, if you enjoy the work that we're doing, feel like it's supported you in some way, we do have a Patreon page. We're super thankful. That said, we're jumping
Links down
into
below.
182. This is a viewer based question. So this was a colleague, a researcher at a university who's doing a lot of simulation work. And they have a big simulation with a nested for loop. And it takes a long time to run. And R being single threaded can sometimes take a long time to run with those things. So today we're going to talk a little bit about parallelization. We've talked about this a little bit in tidy models when we've done some of the tidy models work. And tidy models is great because you can kind of just call do parallel and they set up everything for you within the framework. So it's super nice like that. But if you're building up a simulation from scratch, you're going to need another strategy. And so we're going to borrow from a nested for loop simulation that we did in episode 144. And we're going to show how much faster this can be if we use parallelization.
Yep. There's a link for 144 just up there if you're curious and want to know the detailed explanation of how all this code works. We're going to try to aim to skip over the specific details of the nested for loop and the simulation to get to how do you parallelize this darn thing. So we've got three libraries that we're going to be loading for our use today. So tidyverse for our generic data manipulation needs. The package that we're going to be using for parallelization is one that I'm most familiar with, which is called Snowfall. We know that there's a ton of other packages that are out there to help with parallelization, but this is the one that I am the most comfortable with, the most familiar with. It's not to say it's the only way, obviously, but we're going to show you how to do it in this. If you'd like to see us use do parallel or some of the other libraries, leave a comment down below so that we know that you want to see other ways, or let us know if you've ever used Snowfall in the ways that you've used it. Next, we have the library TikTok, not the app. This one allows us to do some benchmarking, so we compare between the nested for loops versus the Snowfall approach, so we can kind of give you an idea of how this scales up as you go. So the first thing we do is let's set up the situation here. Patrick, what's going on?
Yep. So we're gonna simulate some data that looks basically like this simple table here, where we have a number of subjects, 10 subjects, and we have a few variables, each of different numeric quality. So this is kind of an example table. This is the example output. And from that table, we are going to create models that we want to run on our data. And so in this case, we have a table of 10 rows with 3 variables. And what we want to do is we want to create 3 different models. So we're going to say model 1, model 2, and model 3. Each of them have different output and input variables or dependent and independent variables. So we store that as a vector. And an example of this, we would call each model and run the LM function, so the linear regression model function. And you can see we get 3 results. So that looks cool. That's one time. What if we wanted to do this 1,000 times? In episode 144, what we did was we set up a simple for loop, and it was nested. So we set up 1,000. We're going to start the timer here. So TikTok is an awesome package. I use this all the time for, like, if I'm fitting models like Bayesian models and I want to see, or mixed models, I want to see how long things are running for, and if there's ways I can cut down on that operation time so I can compare things. TikTok, you basically give it a tick at the start of your process and a talk at the end of your process, and it's going to calculate the time spent on that task between the tick and the talk. So we start the timer there. And we're going to create a list for the outputs of the simulated data sets, because we're going to want to store those. And we're going to create an output for the lists of the simulated models. So getting all the information out of this. And this is just a for loop. We're not going to go into the nitty gritty of this, but again, it's a nested for loop. So we have one for loop that's telling us how many simulations we're doing. We create the data simulation, which will be done 1,000 times. We get an output of that, and then we pump that into a second for loop, which is doing all of the heavy lifting to calculate the linear models there in line 62.
Yep.
And it's calling each of those 3 models by index J.
Hmm.
And then it's spitting the output into this list. And then we kind of combine everything into a single output value once we're outside of that middle inner for loop. And there we go. And we're done. And so if we run all of this between tick and tock, again, if you want to know the nitty gritty, episode 144, we run all of this between tick and tock, and it's churning. This is, I mean, think about this. This is 1,000, only 1,000 models.
Oh,
Oh,
shouldn't have printed it all out.
you
Oops.
printed out the entire output. That's okay.
Here.
Yeah.
Will it still print out the no? Where let me run the simulation again without the it printing out all the outputs. I got too overzealous and highlighted the. There we go.
And there we go. So it's about, nearly 5 seconds, right? So 4 seconds and 4.44 seconds. So, it's 1,000. It's a relatively simple model. You could think about if this was something more complex, how long this could potentially take. If we were doing 10,000 iterations or 100,000 iterations, how long something like this could take. It really scales pretty quickly. So 4 seconds on a simple model is too long. So Ellis, walk us through how to use Snowfall to basically parallelize this and make it go faster.
All right, let's. So the first thing we need to do is we need to tell our computer, our system, hey, we're actually going to be running stuff in parallel. And once you've called library snowfall, when you initialize it using sf init, you say parallel equals true. So this is saying, hey, we're actually going to be running stuff in parallel, not sequentially. And then CPUs equals an integer. And CPUs is actually going to be the number of new processes that are going to be spun up and running at that point in time. And that is the potential number of different R processes that can be now running your new parallel contents over time. So I want to caution here, CPUs, you could technically put like 100 in here, even if you don't have that number of CPUs, because it's all the new child processes that occur. However, you're not going to get the benefit of having 100 new processes because your computer only has n number of cores. So,
in Snowfall, I know in do parallel, you can look up num cores. I wasn't sure if there was a way that people could look up the number of cores that they have using Snowfall. Is there a?
I think you can do SF CPUs here.
Oh. You have more than one core.
Yeah. Don't know why it this is telling me the number of CPUs I've initialized. I forget how you actually pull that, but I know that my computer technically has 8 cores, but I'm going to use 6 of them for this parallel.
You could in line like 93 type or in the console type do in lowercase and then capital P parallel dot yeah, and then do maybe it's like num cores or no.
I know there's a way to get it.
There is, and I can't what is the oh well. I know there is a function that lets you determine detect cores. That's what it is. So it's the do parallel detect cores. I think that is that what it is? With a capital C, maybe. Detect cores.
No, not a function.
Yeah,
are you sure it's
I don't know where I don't know. I think it's either there or it's in for each. I mean, those kind of two go together. So anyway,
we can. Oh, this is what we get for not scripting this and practicing this ahead of time for y'all.
That's all right.
But anyway, parallel detect cores, not
is.
do parallel, just parallel.
Parallel detect cores. There it is. Yeah. So this will tell you how many cores you have available. So Ellis has 8, so he could,
I've got an old computer.
He's got an old computer. Instead of 16, he's running 8. Yeah.
Yeah. So forgive my computer for not being the most beastly of computers. But yeah, so we're gonna initialize snowfall using SF init. Say, hey, this is the number of new processes that I want, using identifying with CPUs. Next, we're gonna, just like we normally do at the very top of our R scripts and call our various libraries we're gonna want to be using. Use SF library to then tell your new processes, new parallel processes, what libraries you want to be loading and running um, in those new processes. So you don't have to call library tidyverse a whole bunch of times in your new code there. So we're going to initialize and then we're going to call SF library tidyverse. So tidyverse is going to be loaded in my cluster. Now for timing, we're going to have tick here. The functions that Snowfall makes available are very similar to the base R apply family of functions, except they're going to have SF put in front of it. So what we're going to do here is where you normally would do if you just were using apply instead of the for loop, seek len number of simulations into apply, and you write your function as you would. We do snowfall SF apply, and so now it's going to be using snowfall parallel processing and distribute all the parallel jobs across all of the new systems that we've got, processes we've got running here. We're going to set it up so we have the function. We're going to say the I or the first entry, which is iteration, is the entry from nsims, and then models is the second argument that we add to our function. Those are, remember, the three models that we're going to be running our linear model on. When we initialize our function, we're actually going to want to set a seed based off the iteration. That's going to make it so that each of the parallel processes don't accidentally use the same seed and therefore actually don't give us an independent simulation. By setting the seed to be based off of the iteration number, they're all going to be independent. We then, generate the data set as we did in the first for loop example. We generate our output list. We again go for every single model that we pass in, generate the linear model, and pull out the various pieces of information that we care about. And then because we're running this inside of a function and inside of a apply, essentially, we can't actually just directly write out to contents in our environment. So we're going to return a list of the sim fitted values are the output list, and the sim data set is the simulated data set. And so that way we get a list for every single iteration. That iteration is going to contain two entries, the values from the fitted models as well as the data set that we have. So let's run all of this now using tick and talk.
See what kind of time saver we get here. Wow.
And
So
we've saved
basically
3 seconds
Yeah.
for just replacing that exterior for loop with this snowfall SF apply. And then this is going to scale up too, right? So as we have more CPUs, that's going to decrease this time, as well as we have just it's not going to go at the same linear rate as you would if you had the in series, right? This is going to then bring it down by a scale of n CPUs that you're using. Uh, there's another function you could use instead of SF apply. It's SF cluster apply LB. And the difference between this and SF apply is this is going to be doing load balancing for you. So
Mm.
SF apply will just blindly cut the sequence of values being sent in into even chunks across your CPUs. So it'll take, for here we had 1,000 and we had 6 CPUs, so it took the first 200 or so indexes and set it to parallel process 1, the next 200 to parallel process 2, 3, 4. So it split it up evenly and let it run. The downside of that is if you have high variability in how long it takes for each iteration to run, which could happen with your more complicated models, you may end up with situations where the first 200 or so of your simulations are very time bound and take a lot of time to run, but the other ones run incredibly quickly for whatever, they converge very very quickly, or they're, for some reason, they're easier to solve. So you may end up with situations, if you use SF apply, that it gets caught and is waiting for one of the clusters or one of the processes to finish running while all other ones are completed. So by doing load balancing, there's a little bit of overhead because now it can't just send all 200 jobs off to core 1, core 2, core 3, core 4.
Mhm.
Um, there's more communication happening, but if you have high variability and a high number of processes or simulations to be run, this will load balance it and try to make sure that all of them end approximately at the same time. So there's a benefit to doing that. Not going to do it here because there's not. I mean, we're already at 1.45 seconds. We're already saving 3 seconds, and then
Yeah.
again, as it scales up, we get a lot of benefits. So how do we pull out the values like we did before? So really functionally, it's not very different because the return is just a list. So we end up with, out of parallel simulated outputs, if we want to get the fitted values, we map across each of the iterations, pull out the fitted values, and do a bind rows. And now we're able to see very, very easily the outputs. Here, of course, printing it out is a little bit difficult, but you can see we have
Yep.
the model, sim intercept, sim slope, and because I printed out one of my view wasn't super wide, there we go. We end up with the simulation number as well. So we can have all that information very easily accessible still, as well as if we wanted to pull out the data sets and bind it together, we seek along every simulation. For each one of those, pluck out the simulated data set, add the simulated sim number to it, and we can bind it all together. So that way we end up with, this is for simulation 1, all the way down to simulation 1000.
Yeah.
And we end up with
Pretty
10,000 rows because 10 times 1,000. There you go. That is a very quick and simple approach and demonstration of how you can use Snowfall to parallelize your process that you might have already written to apply, but by setting it up to use sflapply, you've just saved a whole bunch of time.
Mhm.
And
That's
with
awesome.
that, we're going to call episode 182 of TidyX. Thank you all for joining. As always, my name's Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
And my name's Patrick Ward. You can find me on X at OSP Patrick. The screencast is on X at tidy_explained. Of course, YouTube channel, easiest way to hit us up. Questions and comments down below. We do have a Patreon page if you'd like to donate to the show. We are appreciative of everything that you'd like to give.
Thank you all so much and keep on exploring your world.